Welcome to part two of our flip notes on groundwater. And if this slide looks familiar, I hope it looks familiar. It's actually the last slide that we went through in our last video. And I just want to quickly review what an aquifer is. An aquifer is a formation that allows water to be accessible at a usable rate. Now, some people will just say an aquifer is any place where groundwater is stored. I like to think of it as a place where groundwater is stored, but you can pull it up. You can pull it up with a well. It's usable if it's accessible at a usable rate. So if it just trickles out, drip, 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 what can you really do with that? And when we look at Wisconsin, Wisconsin has several major aquifers. In fact, a lot of people consider Wisconsin to have four major aquifers. And here you see a cross section of the state of Wisconsin, and we're going to take a look at these aquifers. The sand and gravel aquifer, and this is really kind of a neat aquifer here. So here you can see it right here. And when we look at sand, sand is really well-rounded, and it's a good place for water to be stored. It's going to be stored in all the porous space, the little gaps, because no two rocks, none of these sand, none of it's going to come together and fill complete 100% of the void space. So in any of those little open spaces, water will sit and water will be stored there. And sand and gravel is a really good aquifer. You have your eastern dolomite aquifer, which is in the eastern part of Wisconsin. You have your sandstone and dolomite aquifer. And then your crystalline bedrock aquifer. So these are the major aquifers in Wisconsin. And you're going to be working with those aquifers in one of the labs that we do. You're going to be talking more about them. Now, what is a confining layer? If I went to you and said, listen, you're being bad today, I'm going to confine you to the back of the room, what would that mean? If you said, well, that means I have to stay in the back of the room, I can't go anywhere else, you're right. A confining layer is a non-permeable, or sometimes another word for that is impermeable layer, referred to as an aquitard, an aquiclude, or a confining layer. And confining layers restrict water movement. So if I said you're confined to your room, that means you're restricted to your room. So a confining layer restricts the flow of water. There are things like clay, shales, non-fractured, weakly porous, igneous and metamorphic rocks that don't let water readily flow through it. So these are examples of aquitards or aquicludes or confining layers. All, aquitards, aquicludes, or confining layers all mean the same thing. And let's talk about groundwater recharge. How do we get groundwater in? We pull it out of the ground, we drink it, we swim in it, we shower in it, we do our laundry with it. But how does it get back into the ground? Well, water is continually recycled through aquifer systems. Groundwater recharge is any water added to the aquifer zone. The processes that contribute to groundwater recharge include precipitation, stream flow, leakage from reservoirs, lakes, aqueducts, and artificial means. There's some locations that actually inject water into the ground. And Green Bay had a situation a few years ago where during the summer months they were running out of water. So what they would do during the winter months is they would pull water from Lake Michigan or the Bay of Green Bay, one of the two, I forget which one, but they would actually pump it and they would pump it into the ground. And it's kind of a neat idea because right now we store water in water towers to use in our homes. Well, they were pulling water out of the lakes, basically Lake Michigan, the Bay of Green Bay, that is part of Lake Michigan. They were pulling that water and they were storing it in the ground during the winter months. So that way during the summer months, there's enough water to go around. And so if that's how they store water and that's how we put water into the ground, how do we get it out? Well, groundwater discharge is any process that removes water from an aquifer system. Natural springs, artificial wells, and those are the ones that we usually put in, are examples of discharge processes. Groundwater supplies approximately 30% of the water present in our streams, which is really, interesting. Last summer, we had a bit of a drought here in Wisconsin. And you could see when the groundwater was low, we knew it was low, the streams were low as well. So here we see some recharge. And again, I apologize because some of these slides just aren't working. And that's one of the, interesting things going from Google Docs from PowerPoint. And it could just be that I don't have a full screen presentation going right now. But recharge, you would be able to see that groundwater is going in and discharge is pulling it out. So this is a really interesting slide. There's a lot of things going on here. We have a recharge zone. And this is interesting because when this water hits the ground, it's going to go into it. And here's your unsaturated zone. But here's an aquiclude or an aquitard. This is where water can't pass through. So when water's coming down here, it'll actually flow off the aquiclude and it will flow out as a spring. And there's another neat, interesting thing here where you have an aquiclude down here. And then when water gets underneath there, it actually could create an artesian well. We'll talk about that in some upcoming slides. Well, it's right here. And artesian aquifers are confined under hydraulic pressure. And the result is a free-flowing water, either from a spring or from a well. So if you get around, you'll actually see some of these in the area. So next time you see water flowing out of the ground and there's not a well or a pump there pumping the water up, there's a good chance it's going to be an artesian well. And here what would happen is, and you can see it right here, I'll move the mouse over it. If this water would go up, right now there's not enough hydraulic pressure to force water up. But if this water would continue to fill higher and higher because there's a lot of rain, eventually water will be flowing out of this pipe. And you don't have to pump it out. The hydraulic pressure will force the water up and out. Here we see an artesian well. Does anybody recognize this one? If you said this is the one in Rock Springs, you're exactly right. And there's enough hydraulic pressure to force the water up and out of here, and it doesn't have to be pumped at all. It just comes out naturally. Now, an artesian well flows continually. Well, let me put it this way. It typically flows continually. Last summer, and there's been some other times, say in the Rock Springs, where we don't have enough water, the artesian well is not flowing anymore. So typically it flows continually. It is produced when a well penetrates the clay layer and the land surface is below the pressure surface. So that pressure forces the water up. And you can see that here in the picture. Now, we actually create artificial artesian wells all the time. Here in Baraboo, we store water in these tall, big tanks, and we call them water towers. And the reason they're so tall is because we want to create enough hydraulic pressure so that water is sitting up high, and that pressure forces the water into all of our houses. And so this water pressure in buildings is maintained by hydraulic head and confinement of water beneath the pressure surface. So it's kind of a nice thing that we can do this, because even if the power goes out, the city of Baraboo has pumps, and West Baraboo has their own well as well, but they have generators that will continually pump water into these water towers. When I grew up, where I grew up, I should say, not when I grew up, but where I grew up, where I lived when I grew up, we lived in the country. And when the power went out, we had no water because we didn't have a generator, and generators weren't common back in the day. But we had to pump the water out of the ground. We're here in the city has the generators. They pump the water up there, and as long as there's water up there, even if we don't have power, we can still use the toilets and we still have running water. Now, spring represents places where the saturated zone comes in contact with the land surface. And again, where I grew up, we had some springs that flowed into what we now know as the Fox River. And the Fox River starts on my parents' property. It's actually my brother's property right now, and it flows through that land. And along the way, you see several different springs. Now let's talk about porosity. Porosity is the fraction of void space, the empty space in soils or rocks. And we know that well-rounded and well-sorted sediments usually have higher porosities than angular or poorly sorted sediments. And this is because the grains don't fit, they don't quite fit together well. And this pore space holds water. You can see that in this diagram. So the more space you have, the more water you have. And porosity, you know, there's some soils or some mediums that have as little as 1% open space or porosity, and there's others that have more than 50%. So the amount of porosity really depends on the material, how it's sorted, and what kind of material it is. Now, permeability is something altogether different. Permeability is the capability of a rock to allow the passage of a fluid. And permeability is dependent on the size of the pore spaces, and this is huge, and to the degree to which the pore spaces are connected. And the reason why this is huge, if we look at this right here, you might look at it well-sorted material, well-sorted, you know, coarse material, well-sorted fine material, permeability and hydrologic conductivity. We know that clay is actually very porous. However, the pore spaces are not connected. And so even though it's very porous, it does not have good permeability. It's got low permeability. And we're going to stop right here, and we're going to finish up part 3 of the notes. I'm hoping to get everything done in part 3. And we're going to talk a little bit more about how groundwater flows and how it might get contaminated in this third part. And the third one may be just a little bit longer, but I'll try and get through it as quickly as I can. As always, if you have any questions, just give me don't give me a call. You can email me, or you can ask me when we get to class. Thanks. Have a good day.